Okay, so if someone could please type hi or something in the chat room just to see if it's working. And then if oh, Gary, thank you so much. And if somebody would like to say hello with their audio on so I can actually see it.
What's up?
Okay, great. I can hear you a little bit. So I think it might be best to use the chat if you can. It looks like when
Yes, sir.
I record, the audio kind of is a little choppy. So I don't know why that is. I'm going to switch Wi-Fi's here, see if I can't help that a little bit. And so, but please keep in mind the chat is going to be probably the easiest thing to do right now. When we have so many people on the screen, I think that maybe my computer's bogging down a little bit. Maybe I should reboot it. Okay, so now that we're here, let me go ahead and do a little bit of administration first. We're going to finish off chapter 11 today, and then we're going to start reviewing. Okay, so I have posted to Canvas the review for chapters 1 through 11, which is the chapters we've had there. And it's kind of like the one I did last time, chapters 1 through 7. In fact, it also has those, plus the rest. And we'll talk about that review and how to use it on next Monday's Zoom meeting. Okay, remember we have a Zoom exam next Wednesday, October 28th. So we do not come to Zoom class. We go to Top Hat and log into Proctorio and do all that. If you've made any changes to your computer system or Wi-Fi since the last exam, please go ahead and ping me and I'll open up a mock exams to get you to try that out to make sure that that will be as low stress as possible when you go ahead and do that exam. Okay, so in addition to that, due this week is our, oh, that's the wrong one. That's not this week. Let's see, what week is it? Is it week 9, 10? What week? Oh, here it is. No, that's the wrong week too. Where's the right week? This is week, where is it? It was just here. We're week 9, October 19th through October 23rd, so that's correct. All right. So the last 2 sections we have is our chapter 9 and chapter 11. Both homeworks will be due Friday, October 23rd at midnight. Okay, and then as soon as you're done with those on that Friday, it'll be open up for review. So you can start reviewing what we have, start re-looking at the different types of slides and the review slides, et cetera, to help kind of schedule your time for studying for the next exam. It's weighted slightly toward chapters 8 through 11, but there will be components of chapters 1 through 7 in there too. So don't just ignore chapters 1 through 7. And if you had some difficulty in one of the chapters, go back and study that a little bit to help reinforce it. So as we move forward, we can add all of the chemistry we're learning all together. Okay. So that is all the administration I have. Again, next week, we're just going to have the 1 Zoom class and then 1 Top Hat exam. So you'll only see that code is good for 1 day and 1 day only. All right, so if there are any questions, go ahead and ping them in the chat, or you can try audio. We'll see how that works. And well, I pull up my slides for today. I'm gonna start sharing my screen. Okay. All right, let me do that and see if I can't get this to work well. Okay, so our goal for our chapter 11 is to look at spectroscopy. And in the first goal, we looked at IR spectroscopy, which is infrared light, and it's just below us, our visible length. And that focused on that energy was being absorbed by bonds, individual bonds, to make them vibrate. So that means that we wouldn't actually see something to say, oh, that's an ester. We would see the different bonds that make up an ester. So we would see a carbon-carbon bond, a carbon-oxygen double bond, and a carbon-oxygen single bond, and then the carbon-hydrogen bonds. And they all show up in different regions, and therefore we can help identify those things. Then we moved on to Proton Nmr Spectroscopy, where we were looking at just the hydrogens. And what we learned in Proton Nmr Spectroscopy is that we were using radio waves in a high magnetic field for us to probe the connections of hydrogens in the system. And what we learned is that if it's one or two, if it's two bonds from hydrogen to hydrogen, or specifically three bonds, hydrogen to carbon to carbon to hydrogen bond, those hydrogens, if they were not identical, they would split each other. And so we looked for a specific splitting pattern, one for the carbon you have, I'm sorry, one for the hydrogen you have, and then N, so the number of different hydrogens that are within three bonds, and that shows you how many splits you have in your system. The other thing we saw in that spectroscopy is that they move back and forth on that ppm scale based on how close they are to an electronegative atom. Like if it was up at oxygen, it was moved up from 1 ppm, where carbon hydrogen would be, to 3 ppm. And then if it had a double bond, it would move up again. So we saw that that's how it was working here. Now, today we're going to look at carbon NMR, which is just the carbons and not the hydrogens. And we have some really good streamlining things where we don't have to worry about splitting. We still have to worry about carbon-carbon connection. But the same way that the hydrogens spread out across that ppm scale based on what they were bonded to, we see that same trend in carbon NMR. Okay, so let's talk about carbon NMR and why it's called carbon-13, okay? So the first thing we have to think about is that hydrogen, proton NMR, which is done with hydrogen 1, the isotope has 1 proton and no neutrons. That's the predominant isomer for hydrogen, okay? So it's in very high abundance. However, carbon is atomic number 6, okay? Which means its predominant isomer is that it has 6 protons and 6 neutrons, which means it has an atomic mass of 12. Now that's 98.9% of all carbon we see is that atomic number, that atomic mass 12. But if you add an extra neutron, you have a naturally occurring isotope called carbon-13. And now that we have a mismatch between protons and neutrons, we now have nuclear spin, and we can see it in these high magnetic fields. So you'll notice that almost both of these have odd numbers in their atomic mass. That is very common throughout the all the different types of atoms that we can see by NMR. Most of them have these odd masses, and that's because that mismatch in the nucleus gives us our ability to hit them with that radio wave and be able to flip them and then wait for them to relax and see where they show up, okay? So unlike proton NMR, we don't have splitting, okay? And the reason we don't have splitting is because the carbon-13 is NMR active, right? So if 99% of your carbons are carbon-12s, there's a very low probability that 2 carbon-13s are going to be next to each other, okay? And if 2 carbon-13s aren't next to each other, they're not going to split. Therefore, we don't see splitting. Another thing that we have going for us is that we actually do it where we can eliminate any interaction between the proton, that hydrogen 1 isotope, and the hydrogen-13 isotope 2. So we don't see the protons splitting it either, okay? So basically we actually run the experiment so that we eliminate all types of splitting, so we don't have to worry about that N+1 rule, and all we have to worry about is the number of peaks we have and the relative location they are on that ppm scale. Now, in proton NMR, we had 4 things to look for. We had the number of peaks, we had the intensity of those peaks, or the integration of those peaks to tell us how many hydrogens there were. And then we had the shift of those peaks, and we had that spin-spin splitting. Okay, so we had 4 things to look for. But in carbon NMR, we do not see, it's not very common that we can actually do an integration. So we don't have to worry about the intensity of the peaks. We just worry about the number of peaks we have and where they are positioned. So we went from 4 things important in proton NMR down to just 2 things important in carbon NMR. Okay, and those 2 things are shift and number of signals. Okay, so that being said, let's go ahead and dig in a little deeper. Okay, so just like in our proton NMR, we need to find things that are equivalent or not equivalent. Okay, so what we need to look for is that if something is symmetrical, are those carbons magnetically equivalent? And so if they're magnetically equivalent, we will see them as different peaks. If it turns out they're magnetically non-equivalent, then we see them as different peaks. If they are equivalent, they turn into one peak. So that's why you can actually have multiple carbons under one peak, because they're all the same kind of carbon. So again, in our system here, we actually take away the coupling between hydrogen and carbon-13. So we have eliminated that splitting pattern, and it makes it easier for us to tell how many different types of carbon we have, and then look at their shifts to figure out which are which. Okay, so let's look at our NMR spectrum that we see. Remember, in hydrogen, our Y scale was intensity, and in this case, it is intensity of these peaks, so our peaks get bigger or smaller, and it's just a relative thing. The actual number does not matter. And then we have on our x-axis what we call our chemical shift. And in hydrogen, it was predominantly from 0 ppms to about 10 ppms, where 0 was that standard, that tetramethylsilane, okay, as our 0. We use the exact same standard in carbon NMR so that we know exactly where 0 is. But in contrast to proton NMR, carbon has much bigger shifts. Okay, so what we'll see here is a typical scale on our carbon NMR goes from 0 ppm to 200 ppm. So that's 20 times larger than we see on a proton NMR. But the relative location of different things attached to electronegative atoms is approximately the same. So let's blow up this end right here and just take a look at it. Okay, so one of the first things we notice about carbon NMR is that baseline right here, where it just starts here, instead of being a nice flat line, like in proton NMR, and then nice little, peaks like that, we see this fuzzy baseline. And this is because, number one, carbon-13 only appears at 1.1%. So we have much, much less of it. And carbon is actually 4 times less susceptible to the signal, meaning its signal is even 4 times less. So it's 4 times less, plus there's only 1% of it. So that's why these are a much noisier spectrum. It's very much harder to see. But we do see them, and they do have these nice clean peaks. Now, the second thing we see in this particular one is actually the solvent. This solvent right here, this particular one, DMSO, which we learned about as a polar non-protic solvent in Sn1 Sn2 reactions. It actually shows up as multiplets and multiplets because there is so much of the solvent in there that it shows up. Okay. And then the next thing we see is the peak of a unique carbon. Okay, so that carbon is specifically one type of carbon on our system. But when we look at our structure, we have to look for things that are identical with connections and things that are not identical connections. If they have identical connections, then we have equal carbons. And if they're not, we have separate carbons. Okay. So that's what we have when we break this down. And notice that we have peaks that are way up here. And then we have peaks way up here, okay? So those must be different kinds of carbons right here. And then if we looked at the spectrum, we'd say, okay, we have one type here, 2, 3, 4. So we have 4 different kinds of carbons. Does that mean we have 4 carbons in our structure? No. We have to look for symmetry, but we have 4 different kinds of carbon in our system. Okay, so that being said, we are looking for different regions. So in our first region, we have things that are down here are going to be, I'm sorry, to about here, are going to be things that are, you know, carbon bonded to carbon bonded to carbon, okay? And they can have 1, 2, or 3 hydrogens on them. They're going to be down in this range here. Once we get into this, let me change the color here. Once we get into this range here, these are going to be a carbon bonded to an electronegative atom. So oxygen, nitrogen, halogens, those are going to be things like that. Just like in Proton Nmr, we have our carbon hydrogens at the low end. We have things that are starting to have our electronegative atoms. Then our next zone is this zone here, which is where we start seeing carbon-carbon double bonds. And in particular, this zone here is where we see benzene rings show up. And then our last zone way up here is where we see carbon oxygen bonds or carbonyls. Okay, so those are the 3 different regions you'll find each and every type of carbon in a carbon NMR. We start with the most hydrocarbony stuff down here at the low end, things that are attached to oxygen, nitrogen, and halogens. And then we start with the double bonds, including the benzene system and then carbonyl. So knowing that, just looking at our spectrum, we have a kind of carbon that looks a little bit like an alkane right here, just an alkane, carbon hydrogen section. Let me redraw that. So that's going to be, we're looking for something that looks kind of like an alkane, a carbon hydrogen bonded to a couple other carbons. That's what we're looking for there. Now, the next thing we see here is we see something in this other range here. So we're looking for something that a carbon bonded to like an oxygen or a halogen or something like that. I happen to know there's oxygen in our compounds, so we're looking for those kind of things. But again, this is going to be a carbon with hydrogens on it or other things bonded to it. It's not going to be a carbon that has a carbonyl on it. And then the last thing we have here is we have these 2 peaks over here, and they're both in that carbonyl region. What that means is I think we have something that we have 2 different types of carbonyls. Okay, so we have 2 different peaks, so we have 2 different types of carbonyls. So now let's look at our structure and see if we can't identify each and every one of those. Okay, so our lowest one was A, so that's the most like hydrocarbon. Our lowest was B, that's most like a hydrocarbon. And if we look at the structure here, switch over to that color right here, this B1 looks most like a carbon with hydrogen on it, bonded to 2 other carbons, okay? So that means this structure right here is going to be the one that's the lowest at the end, okay? Because it's a carbon with hydrogens on it, bonded to 2 other carbons. It's most like an alkane. Okay. So if that's our lowest down, then our next one is going to be a carbon with kind of maybe carbon and hydrogens on it, but then bonded to electronegative atoms. Okay. So what we see here is we only have 1 carbon that's bonded directly to an oxygen or a nitrogen. So this carbon is bonded to this oxygen here, and then it's bonded to a carbon here, and carbon here. So those don't count to change the shift. Only the bonding to oxygen helps change that shift, which means this one right here must be C, because it's the only one that has a carbon-oxygen bond. Okay. Now, we had 2 different carbonyl peaks, okay, and they were in different places, okay? So that means that this, remember that our COOH looks like this right here. So we have a carbonyl and an OH on it. That means that we have 2 different types of carbonyl. Okay. So, and if we look at D right here, if we look at this top one right here, This has a COOH bonded to a CH. Okay, so okay, that's our starting point. That's one type. We'll call that type A. And then we have this one right here, a COOH bonded to a C, but with no hydrogens on it. So that's different. So we have to call that B. And then we look at this last one here, and we have a COOH bonded to a CH. That looks exactly like A. So that means that these two are one of those carbonyl peaks, and this is the other carbonyl peak. So when we put it all together, we have 4 types of carbon in our system. Even though we have 6 carbons, we have 4 types of carbons, and we can identify each by what they are attached to. Okay. So let's look at what kind of zones we have and what some common themes in those zones are. They trend exactly like we see in Proton Nmr, but they have bigger ranges. So the first range I want to talk about is our Sp3 hybridized carbons. So it's most like an alkane, right? And the other thing is that a tertiary carbon, one with no hydrogen, only one hydrogen or only one hydrogen on it, are going to be higher up. So the tertiary carbons are going to be closer to 50. The ones with 2 hydrogens on it are going to be in the middle, in the 30, and the one with 1 hydrogen on it is going to be toward the bottom, let's say 10. Okay, so even with just those shifts, all Sp3 carbons, you can tell because of the shift how many hydrogens they are. The more like methane, the closer to 0 it's going to be. We substitute one of these for a carbon right here, it now shifts up to 10. We substitute another one for a carbon, it shifts up to 30. Substitute another one for a carbon, it shifts up to 50. Okay. So that being said, so that's the lowest end. That's that low end, that type 1, the hydrocarbon-like. Now, the second thing we see is that when we move up, we go into this range of 50 to 80, right here. So these are things where we have electronegative atoms like nitrogen, oxygen, chlorine, fluorine, bromine, etc. Okay, so these are all going to have that higher chemical shift. And so those are up into the 50 to 80 range. So that's only 30 ppm. So that's a good place for us to see all those. Okay. Then the next thing we see is our Sp2 hybridized carbons. So that's all carbon-carbon double bonds and our benzene rings. Okay, in this 100 to 110 range. Now, our carboxylic acids, because it's a carbonyl, but it has that electronegative oxygen here, is the next band, 160 to 180. Okay. However, carbonyls that don't have these oxygens on them, right here, carbonyls like aldehydes and ketones, are actually higher, 180 to 210. Okay, so we can not only tell the difference between primary, secondary, and tertiary carbons, we can tell the difference between Sp3 and Sp2 carbons. We can even tell the difference between different types of carbonyls. The carbonyls that are carboxylic acids and derivatives are lower than those of aldehydes and ketones. Okay, so let's apply all of that knowledge to these structures here. So the first thing we want to look at is how many different types of carbons we have and where do we think they're going to show up based on what they look like. Okay, so let's start with this one right here. Okay, now if you want to get this straight in your head and draw it out in your mind to make it look like OH. If we draw it in the skeletal structure here, okay, we have one type of carbon that's bonded to an electronegative atom. So we're going to call this one A. Okay. And then we have another kind of carbon here that's a carboxylic acid derivative. So that's going to show up in a different place. And then we have our last kind of carbon here. It's the most hydrocarbony looking of the set. Okay. So we expect to see 3 signals because we have 3 kinds of carbon here. Okay. So let's kind of predict where we think they're going to show up. So because this is most like the hydrocarbon, we expect to see this between 0 and 50 ppm. Okay, because it's kind of like that. In fact, because it's bonded to this carbonyl, it's going to be shifted a little bit higher toward that 50 ppm, but it's in that range always. Okay, if we look at this carbonyl here, remember a ketone and an aldehyde is 180 and to 210, okay? But this is a carboxylic acid derivative, which takes us into the 160 to 180 range, okay? So we expect to see that carbon there, okay? And then our last carbon here has an electronegative atom on it. So we expect to see that between 50 and 80 ppm. Okay, do we see what's going on here? Okay, we can pick out each zone of the section just based on what the carbon is attached to. Just like we did the same thing in Proton Nmr, we looked at what the carbon was attached to with the hydrogens on it, and then we knew that those hydrogens were going to shift based on those same types of connections. Notice the range is much bigger in carbon, but the general trend is the same. Okay, so let's go to this one right here. We might be tricking ourselves, but let's kind of play around with this, see if we can't figure it out. Okay, so we have a CH3 and a CH3. Okay, so are those identical? So let me go ahead and chime something in the chat room here. Are those 2 CH3s identical? CH3s. No, they're not because of connection, right? So this one's connected to a carbonyl, this one's connected to a CH2.
They wouldn't because it's connected to the carbon and oxygen, right?
Correct. That carbonyl is a different functional group and therefore they are not the same. Okay, so that makes this one kind of carbon. So I'm just going to call that one A and this one B. They look the same, but they have different connections. So they are different things. Okay. So let's look at this one. Okay, these are 2 CH2s. Are those equivalent? I see all of you nodding your head no. Okay. So that being said, that's correct because this is attached to a carbonyl and this is attached to a carbon. This is attached to a carbon and a carbon, so a CH3 and a CH2. Therefore, they are all unique, okay? So this is gonna be C, D, and this carbonyl is a carbon. We would not see that carbonyl in Proton Nmr, but we do see it in carbon Nmr. So this is our E right here. So we expect to see 1, 2, 3, 4, 5 different peaks, okay? So let's kind of predict where they're going to be, okay? So of those little peaks here, let's start with this one on the end here, right here. It is the most like a hydrocarbon. So I think it's going to be the lowest number, okay? It's got 3 hydrogens on it. It's attached to a carbon with CH2, CH2. Therefore, it's going to be the lowest number. So in the 0, it's going to be in the 0 to 50 range. So we're going to put this at its lowest number. Just let's say it's 10 to give us a relative term, which means that as we move over here, we now have a CH2. We know that's going to be shifted up because it only has 2 hydrogens on it. So we can predict this to be, let's say above that, 20, okay? And that we know that this one right here is going to be above it because we have a carbonyl on one side and this is the other. We still have the 2 hydrogens. So we can predict that to be closer to, let's just call that 30, okay? Because we know it's going to be higher. Okay. Now the carbonyl. So the carbonyl is in its ketone state, right? So where do we expect to see that? Is it going to be 50 or is it going to be different? It's going to be very high. It's going to be between 180 and 210, right? Aldehydes and ketones are both that far up. And then with our methyl group here, it's a methyl group, but it's attached to a carbonyl, so it's going to be shifted up. So it's probably going to be about the same here, maybe in the 30-ish range here. But we still have 5 unique peaks, but we can pick out exactly where we expect each of them to be. Okay. All right. Now let's go to this last one here. All right. So we kind of already have some ideas about what's going to happen because the last one we analyzed, we know we have a carbonyl here. So we know this one's at least going to be in the 180 to 210 range. Okay. But how many peaks are we going to have? We have at least one for the carbonyl. And then we have a CH2, a CH3, another CH2, and another CH3. So we could have at most, go ahead.
It would be 3, right?
It would be 3, exactly, because we have symmetry. These are identical connections. And these have identical connections. So we are going to see 3 carbons, okay? Now in Proton NMR, we only saw 2 peaks, one for this. In Proton NMR, we would have seen one for this one and one for this one. And they would just be mirror images of each other. So they would be just 2 peaks. In carbon, because of the carbonyl, we have that 3rd peak for the carbonyl. Okay, so we're going to be at our, 180 to 210. This is going to be closer to 50, and this is going to be closer to 20, or sorry, 10, because it's so far down. Okay, so do we see the trending of this? And actually, do you see that carbon NMR is a little bit easier than proton NMR? Because all we have to worry about is the different types of carbons and what they're attached to. Okay, so let's talk about where the actual shifts lie. And we're going to use that exact same trend we talked about, but we're going to see where the actual characteristic shifts are. So our CH3s are going to be our lowest shift. Okay, so if there was nothing but an alkyl group over here, it's going to be closer to 0. However, because we can have, if our R is something like a carbonyl, that'll shift it higher to the higher end. But if our R is just a straight chain alkane, it's going to shift to the lower end. Okay. But our CH3s will always be the lowest carbon in any set we have. Okay. So the next thing we have is our CH2s. Our CH2s are going to be shifted a little above that, 15 to 55. So you can imagine just adding 15 to each of those numbers, you get about that same. And that's because you have the ability of the carbons on either side to help donate electron energy. So it changes that shift a little bit. And then once we get to the next one with a tertiary right here, that means we have 3 different carbons adding to it. So it shifts it up again to give us this upper range. So now we have our CHs, our hydrocarbons on sp3s, sp3 carbons with hydrogens on them from the 0 to 60 range. Okay. And again, the more hydrogens, the lower the number. Now we shift into our halogens, and our halogens have our first electronegative atoms we have. And iodine, because it's so big and fluffy, it doesn't shift it very much. Okay, it's like it was a methyl group, okay, because it's so big and fluffy. However, as that bond between the carbon and the electronegative atoms gets shorter and shorter, our shifts keep bigger and bigger. Okay, so iodine's the biggest, which has the longest bond length. Bromide is next, and so it shifts it up a little bit. And then our chlorine shifts it way high. Look at that, all the way up to 80 here. And then oxygens right here can shift it all the way up to 80 as well. So whenever we have an alcohol in there, we're always going to see it in the 40 to 80 range. Or when we have ethers, because the ethers will do the same. This hydrogen doesn't really play a role in our carbon NMR shift. Okay. So I'm going to do our zones here. Let me go ahead and there we go. Do our zones by color here. So we have our Sp3 hybridized hydrogens, hybridized carbons with hydrogens on them. We have our halogens, C bonded to X here. And then our next zone here is our carbon bonded to oxygen zone. Notice both of the things in carbons bonded to oxygen are this 40 to 80 range. Okay. So then the next zone we have is when we have carbon-carbon triple and double bonds. Okay. So now we've switched from our Sp3 hybridized carbon to an Sp2 or an Sp. Okay. Now, because of the ability to be able to donate and stuff, our Sp hybridized carbon is below our Sp2 hybridized carbon. Okay. And so that's one of the things that might be a little hard to see, but this Sp is below that. But then we go up to our bigger range, and there's a wide range of ways to connect our Sp2 hybridized. And because of that wide range to connect things, including aromatic rings and conjugated and non-conjugated, et cetera, our band is actually pretty high up and pretty wide. It's about 50 ppm wide. Starts at 100, goes to 150. Okay. Now, once we start getting things aromatized, it shifts it up just slightly. So that means benzene carbons are just slightly higher, but notice they're in that same approximate range of 100 to 150. Okay. Now, that's all the different carbons that can have hydrogen on them. Now we're going to shift over to the ones that have carbonyls. Now, if you have a carbonyl and then you have an electronegative atom on them again, these are all carboxylic acid derivatives, and I'll show it from 160 to 185. Okay. So that means that they are above benzenes, but below aldehydes and ketones in their own unique area. Okay. And then our last zone, of course, is where we have our ketones and aldehydes by themselves, and it's our highest zone at 180 to 210. Okay, so that is carbon NMR in a nutshell. Okay, so to review again, proton NMR, we have 4 things to look for. Number of peaks, intensity of peaks, which tells us how many hydrogens we have, shift, and splitting, hydrogen-hydrogen splitting. In the carbon experiment, we remove carbon-carbon splitting and hydrogen-carbon splitting such that all we have is number of peaks and position of peaks. Now, just like in proton NMR, we have to worry about symmetry and what are equivalent and not equivalent for the system. Okay, so that is my last slide for goal 3, carbon NMR. So, any questions on that? Okay, I'm going to stop sharing and see if there are any questions for that. And then I want to pull up one other thing that's new. And then if you don't have any questions, I'll go ahead and go on to the review that's now posted in Canvas and how to use it, okay? Just like last time, I wanted to kind of lay out the important topics, but don't just say study the sheet. You want to use this, do I understand what each of these things are? So I'm going to go ahead and share that and start with, let's see, there we go. How to start studying this. And so one way to do this study is to just say, okay, well, what did I get wrong on my homework? Let's start there. Make sure I understand what I got wrong and why I got it wrong, and then figure out how to get it straight in my head. So when we looked at chapter 1, I stressed the idea that we have Sp3 hybridized carbons, Sp2 hybridized carbons, and Sp hybridized carbons, and they all have different shapes and they all have different reactivities. And so that shape and hybridization started in chapter 1, but we're still using it. We just used it in our carbon NMR as well. Okay, so knowing our functional groups, these are our primary functional groups. We've gotten all the way up to benzenes, and we're going to go to carboxylic acid derivatives and aldehydes and ketones next after the exam. So what we want to do is, still keep these ideas of what our functional groups are, because we talked about each of these functional groups in our IR studies, as well as our NMR studies, as showing that having that electronegative atom on that carbonyl can shift it up, or having an electronegative atom on that carbon shifts it as well. Okay, so again, knowing your functional groups is pretty common. Okay. The relative pKa scale, I picked out 6 of these compounds that you should, be able to rank in order of acidity and know which is more acidic and which is least acidic. The other cool thing about this table is that if it's a weak acid, once you take a proton off it, it is a really, really strong base. And the opposite is true. So that means that when we had HI here, it's a very strong acid, but that makes iodine a very weak base. It's gonna not act as a base, it's gonna act as a nucleophile, and we can use that to our advantage when we're talking about Sn1, Sn2. So this pKa scale actually helps us decide what reactions are going to happen in our substitution and our elimination reactions. Okay. If you have one definition for an acid or base, make it the Lewis acid-base definition because it applies to all. A Lewis acid accepts electron pairs. It's got a partially positive charge, or it's got a full positive charge. Okay, and if we draw out the Lewis-Strauss structure, if it doesn't have a full octet, or if it has a positive charge, it's probably a Lewis acid. Excuse me. In contrast, if it has a lone pair or a negative charge, it's probably a Lewis base. And Lewis bases are nucleophiles. Lewis acids are electrophiles. So we can use those exact same definitions in our reactions, in our acid base, and to know which way the reaction equilibrium lies. Now, Bronsted-Lowry is important because we are talking about the transfer of a proton. But in that case, the proton is the one accepting the electron pairs, meaning the proton is the Lewis acid. And the base is the one accepting the proton, which is the base is the one giving its electrons to the proton to pull it toward it. So it's still the same, but we're actually transferring a hydrogen, where a Lewis acid-base reaction doesn't have to. Then we did a lot of nomenclature. And the different classes of nomenclature have, double bonds, triple bonds, arenes. They all have their own names and such. And so we need to know how to do that. But we also need to remember these common alkyl groups: the methyl, ethyl, propyl, isopropyl, butyl, isobutyl, sec-butyl, and tert-butyl, because those are very commonly used, and it makes it very fast to communicate what those different groups are. All right, nomenclature. These are the basic rules of nomenclature. And the first rule is identify the functional group and their priority. And then all the other ones are the find the longest chain, find the lowest number, find the substituents, and all the different ones, including the stereoisomer rules, which I put here. What's R and S? Okay, what's E and Z? Cool thing is we determine R and S and E and Z. E and Z is on our alkenes, but it uses the same prioritization system that we did for our chiral carbons of R and S. So we use that same atomic number, what's attached to it, and then eventually you have to go to double and triple bonds if that doesn't solve itself. Remember, in those priority rules, you use the rule that gets you the differentiation. If you can stop at number 1, you're done. You don't have to use them all. Use them until there is a difference. Okay. And then remember, cis and trans is similar to E and Z, but E and Z must be used when you have more than 2 substituents. Okay, so cis and Z are the same. They mean the same side. E and trans mean the opposite side, and they're similar in look. And then don't forget R and S, clockwise, counterclockwise. Okay, so the first rule is prioritization. So here is the precedent of different functional groups. Knowing that, the first functional group we chose that actually changed the name of the compound was an alcohol. But then we have aldehydes, ketones, and then carboxylic acids, which we'll study next, actually have the highest priority. So if you see a carboxylic acid anywhere in a function, it's probably named for that. So you can dissect any chemical name using these 3 rules. The prefix, which tells you the number of carbons. The infix tells you if you have single bonds, double bonds, or triple bonds. And the suffix tells you what class of compound it is, meaning if it's a hydrocarbon, it's an E. It's just an E at the end. If it's an alcohol, it's all. If it's a ketone, it's own, etc. And so those suffixes have the infixes are an, een, and ein. The suffixes are E for hydrocarbon, and then own for ketones and carboxylic acid. Okay, so knowing these rules and knowing how to apply them, I know we did a lot of nomenclature, and there's probably going to be a nomenclature or 2 question on the next exam. Okay. Know the difference between primary, secondary, tertiary, and quaternary carbons. Notice we used those definitions when we were looking at NMR. So we're going to continue to use this definition again and again. Okay, and alcohols have a similar nomenclature. What is the priority on the carbon the oxygen is bound to? That way you can only have methyl primary and secondary. You cannot have a quaternary alcohol because then you would have 5 bonds to carbon. Okay. Amines are backwards. It's how many carbons are attached to the nitrogen. So if you only have 1 carbon attached to the nitrogen, it's backwards. Amides are similar in the fact that you have how many carbons are attached to it. But always the first is the carbonyl. And then when we go, now amides are a carboxylic acid derivative, and we're going to learn how to make them and break them in a couple chapters. All right, alkenes. We have basically one thing we do to alkenes, addition reactions, okay? We can add acid across that double bond. We can add water across that double bond. We can add 2 halogens across that double bond. And then we can add hydrogen across that double bond. Or in the case of this one also, there's boron right here. Okay. And then the acidity of the different alkanes is tied into chapter 2. In chapter 6, we learned about mechanisms. There's only 5 things we can do in a mechanism. Add a proton, take a proton away, react as an electrophile, nucleophile, rearrange, i.e. carbocations, and break a bond to form a stable molecule or ion, i.e. carbocations. If it happens all in one step, that's a bimolecular reaction. So those are Sn2 and E2s. If it happens in 2 steps, that means that you formed a carbocation first and then something else happened. Carbocation stability and rearrangement. Okay. The more substituted the carbocation is, the more stable, and it will try to rearrange from a secondary to a tertiary whenever possible. It can do that by moving a hydrogen or a methyl group. Okay. Then that brought us into chapter 6, which is stereoisomers. We have two kinds. We have double bonds, which have stereoisomers, which is E and Z. But then we have chiral ones, which are enantiomers, which are Sp3 hybridized carbons that are mirror image, non-superimposable. Those are enantiomers. That happens if you have one stereocenter. If you have two stereocenters, you have the possibility for more. You have the possibility for up to 2 times n of the number of stereocenters you have. But you don't always have 4 diastereomers, because you can have a mirror plane in that next compound, and that turns it into a mesostructure. So for this particular compound shown here, we have only 3 different isomers. 2 of them are chiral, and 1 of them is not chiral because it's meso. All right, and then we have our Sn1 Sn2. Okay. Sn1 means you formed the carbocation, so that means you need a poor nucleophile and a good leaving group. Sn2 means you had a good nucleophile and not too many things blocking it. So we look at sterics and electronics whenever we look at the Sn1 Sn2 reactions. And when we substitute those, we can make a bunch of different functional groups. Depending on what you use as a nucleophile, we can make all these different functional groups depending on the nucleophile. All right, and then that's summarized into this table here, okay? You have this where, for example, once you have a strong bulky base like T-butoxide, only the methyl group is going to do any substitution. Everything else is going to do E2. Once you get to anything that's a secondary or tertiary in any strong base, it's going to try to do the elimination unless it's a very unhindered primary. Then you can get substitution. Then we move on to weak bases. They try not to eliminate at all. And therefore, our substitution products are going to rule. And then if we have poor nucleophiles, that means we had to wait around for a carbocation to form. And therefore, we really don't know what's going to happen because it had to form that carbocation, so it could eliminate or it could substitute. And they're always in competition. Okay. In chapter 8, we learned how to make alkenes. And we learned a couple different ways to make alkenes. One was to dehydrate something. You basically remove water to form that alkene. But we tried to always form the one that had the highest number of substituents because it was more stable. That's the Zaitsev rule. Then we learned we could oxidize our alcohols to give us aldehydes and ketones. Primaries will give us ketones no matter what carboxylic acids, no matter what oxidizer we use. However, if we have a primary and use PCC, we can stop at the aldehyde. Secondaries, doesn't matter what oxidizer you use, you'll always get a ketone. And tertiaries don't react at all. There's a misprint there. That should be a tertiary. Right here. And then one other cool way to make alcohols is to ring open epoxy. Any nucleophile attacking is going to give you your alcohol on one carbon and your nucleophile attached to the other carbon. Then benzenes. Right. So benzenes are benzenes because of aromaticity. Aromaticity had those 4 rules. Must be planar or near planar. Must have a continuous P's all the way around the ring. Must have the correct number of electrons. 2, 6, 10, etc. And it must, flat, continuous, planar, and electrons. Those are all 4. Yes. Now that you have this aromatic ring, it wants to stay aromatic. So we don't do substitution reactions. We don't do addition reactions on them. We do substitution reactions. And because it wants to be that aromatic range, we have new names for them. Benzene is that cyclohexatriene, but it's not cyclohexatriene because it has that aromaticity, which makes it a new, different reactive species, benzene. And then once we have attachments to them, they all have new names, and those new names are what you're going to name it for. So if your benzene ring has a functional group on it, that changes the priority. Now the benzene is the predominant thing you name for. And then remember that if you have two things on your benzene ring, if it's 1,2, it's ortho, 1,3, it's meta, and 1,4, it's para. Okay. We use the same mechanism on all the substitution reactions, but the first step is to form the electrophile. And the electrophile is something with a positive charge. So we typically use Lewis acid catalysts. So here the iron chloride has to react with the chlorine first to create a positively charged chlorine before it will react. And then it does the addition, and then it kicks out a proton to re-aromatize. Every single step is like that. And then we can do it where we can even make a carbon-carbon bond with alkylation or acylation using a Lewis acid catalyst. Again, the mechanism is the same for all of them. Generate that positive charge. That positive charge is attacked by the electrons of the benzene ring. That charge moves around the ring until it can kick out a proton and re-aromatizes the ring. Anything with a lone pair will stabilize that intermediate and therefore activate the system. Anytime the system is activated, it's going to be ortho-para direction. It's going to be directed to the number 2 position or the number 4 position. Okay. Now, even though these halogens are inductively electron withdrawing, they have lone pairs, so they are active. They are ortho-para directors. All the meta directors have a partially positive charge or positive charge on the atom touching the benzene ring. They all do, and therefore they are all deactivating, and they're all meta directors. Okay. And then amines, we really didn't do that much with amines. They were a very short chapter, but we learned about aliphatic amines and how they're named primary, secondary, tertiary. We learned about aromatic amines, and those are ones where the nitrogen can donate to the pi cloud or not to the pi cloud. And then we had heterocyclic amines, which were where the nitrogen is actually inside the ring, and it could be aromatic or non-aromatic. We also learned that the aliphatic amines were more basic than any of the other amines. And because the bond difference between hydrogen and nitrogen is not as polar as oxygen and hydrogen, they did not hydrogen bond as strongly as alcohols. Okay, and then this, I think, is a great summary of IR. Okay, we have 4 bands where we look for things and everything follows suit. Heavy and light atoms are in this top 25 to 4,000 range. Triple bonds are in this range. Double bonds are down to 1,500 to 2,000, and then all the single bonds are below that. So again, we're not looking for a specific functional group. We have to draw the entire compound out and look for what is in the compound. So, for example, this thing right here, we're going to have peaks in different areas. We're going to have this hydrogen is going to be in our zone 1. Let me color code the zones real quick here. Red, green, blue, and then black right here. Okay, so that being said, we expect to see this in the red zone. We expect to see this in the red zone. We expect to see nothing. Well, oh, we also have hydrogens here. So we should see 3 different peaks in that top zone because of those different areas right here. In this particular compound, we have 1 triple bond. We expect to see a peak in that second zone. In the third zone, we expect to see a peak for this third zone right here. And in our last zone, if we were looking for it, we would see this peak. We would see this peak. We would see this peak right here. So we would expect to find each and every type of bond in each of the zones. And if we add them all together, we can come up with the general, at least the number of different kinds of bonds we have in our system. So it's not about identifying a pure compound, it's about identifying the different types of bonds and where they appear. Okay, which brings us to Proton Nmr. And again, those 4 things. Number of signals, because we have to look for unique places. So if things are symmetrical, it's going to get simple. If things are not symmetrical, it's going to have more signals. So you have to look for equivalent hydrogens. Then we have to look for the number of hydrogens in each of those types of hydrogens, and that's our intensity. And that's signified by that little integral right there. Then we have position. Position shifts with, just like we saw in that Sp3 hybridized hydrogens, Sp2 hybridized hydrogens, aromatic hydrogens, and then hydrogens on carbonyls way up. And then hydrogens next to things bonded to oxygen are up. Hydrogens next to things bonded to halogens are in the middle, et cetera, et cetera, et cetera. So they have that same general shift. We need to think about where they show up in general in our shift. There's also 4 components on our spectrum here. We have our ppm scale, we have our intensity scale, and we hopefully have our standard right here. And then when we typically would have the other components would be the number of splitting here tells us how many hydrogens are on the adjacent carbons within 3 bonds. It has to be within 3 bonds or they don't split. So we know exactly how many hydrogens are in those 3 bonds away because of our N+1. N is the number of hydrogens on those adjacent carbons. 1 is for the hydrogens on that carbon. Okay, and then carbon NMR gets a little bit simpler because we don't have to worry about splitting. All we have to worry about is unique types of carbons, right? So that gives us a number of signals. And then the relative shifts to those signals are analogous to the relative shifts we see in Proton NMR, where the more hydrocarbon-like, the more we're going to be down here. As we change, we're going to move over to get to things that are near things with oxygens on them, things bonded to oxygens, and then carbonyls up here with our aldehydes, with our esters and our carboxylic acids here, and our aldehydes and ketones way up high. Okay, so using this as kind of your study guide, look to not only, oh, that's familiar, but oh, it's because. And the more you study it and you look at the homework and say, oh, okay, why is that? It's because of this. And if you can go through and identify why with a sentence or two about why the correct answers are the correct answers, you are getting much closer to having that being able to answer all the questions with, oh, this question looks a little bit different. Oh, he's asking it backwards. I need to look at it from the other way. So the more familiar you are with the topic, the more likely you are to see what the question's actually asking and be able to translate it from that. All right. Are there any questions about the review or about that? I will be doing this again on, I will be talking about this and I will be giving examples from each of those sections on our review on Monday. So I'll kind of pull up a homework question that looks like that, and I want to attack it from a couple different ways, kind of give you an idea of how to read a question, attack a question, and apply the knowledge you have. Okay. All right, I'm going to go ahead and stop sharing. If anybody has any questions that they want to ask before I stop recording, go ahead and ask that. I think the audio clears up when I stop recording. So if you have any questions right now, go ahead and try. And
I have a question about the homework 10.
okay. Homework 10. Okay, I heard homework 10. All right, here, let me stop recording and then you can ask your question, okay?